Welcome back, Eigen families. So we are back again, and you see we're back in the old headquarters.
Yeah.
So guys, just make sure to like, share, comment, subscribe if you have not already. Check us out on Twitter. Check us out on Instagram. On what else do we have? On website. TikTok.
Eigenbros.com, TikTok.
Yeah, so that's Eigenbros, and then Eigenbros2 on TikTok, Eigenbros everywhere else. And then thank you, patrons, once again. We greatly appreciate it, guys. And if you're interested in some more podcast stuff, 30-minute audio podcast on our Patreon every week, just go ahead and subscribe to patreon.com/Eigenbros in the description as well.
Yeah.
And so today we're going to be talking about an interesting little theorem some of you guys may have heard of. Or I guess not a theorem, I should say a branch of physics pretty much.
Yeah, it's a whole branch.
Yeah, called quantum field theory. So, yeah,
It's
I guess.
lot.
Yeah,
It's a lot, man.
it is.
It's a huge undertaking. So please quell your expectations. This isn't gonna be like a thorough. I would say not that thorough introduction. It's going to be sort of a walkthrough, maybe.
Well, I hope to
Right?
give people kind of a intuitive / broad kind of understanding without going too heavy into details.
Yeah.
And I think we can do that.
Yeah.
But yeah, I mean, it's definitely a big theorem.
Yeah.
Or a big branch of physics, so
Yeah,
it's
'cause
difficult.
I want to kind of give you like some basics, or from my takeaway from this is like give away some basics. Like sort of low level, like kind of understanding of what QFT is supposed to be, what you need to study QFT.
Sure.
And yeah. What about you? What did you kind of want the listeners to?
Well, I was hoping to give people an understanding. Really, one of my main goals is to try to give people an actual understanding of the math and how to do QFT. So, of course, audio podcasts suck with math. So I hoped I found enough videos that were kind of more, more about the conceptual, that you can explain it conceptually rather than getting too bogged down in mathematical details.
Yeah.
So anybody listening to audio, hopefully this is
Please find the link.
at least enjoyable.
Please find the YouTube link.
Yeah, it might help if you can find the YouTube link, but I'm gonna try. We gotta try to keep it friendly for audio people as well.
So first off, Terence, how would you define a field?
Shit, man, you're quizzing me.
No, I'm kidding. No,
You can ask me that. I'll answer.
There's a couple sources that I was looking at, and I'll put them down below.
Yeah.
There's a couple books that I was looking at in the meantime, and I'm sure we'll have a follow-up video because there's still a lot to.
Maybe I won't promise anything. But, I'm sure we will.
I will promise this. No, because it's been a while since I've been wanting to do QFT, and yeah, all you really need for QFT is, according to the books themselves, you need to know Lagrangian formalism, special relativity, and quantum mechanics.
Yep, accurate.
And let's break it down. So what do we mean by Lagrangian formalism?
So the Lagrangian is basically this magical formula that can solve the equations of motion for many different systems. I was first introduced to it in classical mechanics, as I'm sure you were as well, Juan. I think most physics curriculum does it that way. Although you can use Lagrangians in things like quantum field theory. You can also even use Lagrangians, strangely enough, in regular quantum mechanics, although I don't think it's really taught as something normally. And there might be some fanciful things there. I never learned it. But anyway, Lagrangian is basically this magical formula, just long story short. And it's involving the action, which is this really crazy concept. So you can go real deep into Jesus. You can go real deep into the Lagrangian, and you can learn a lot of shit, higher level, real abstract shit about physics.
Yeah. You get the equations of motion from that. We are comfortable with doing Lagrangian mechanics just because we were using it for almost 100 years, right?
And the thing is, it's kind of like the
mechanics.
master equation of everything.
Yeah.
Like if you get a Lagrangian, you know everything about the system basically. Like the standard model Lagrangian is the equation for the entire universe basically.
Yeah.
Except of course
Equation of
it's
motion.
incomplete, right? Or else we would already have a theory of everything. But the Lagrangian that we have for the standard model is like the master equation, and you can have those for different fields. You can have a Lagrangian for E and M. You can have a Lagrangian for classical systems. You can have all kinds of Lagrangians, and they give you everything you need to know about how the system dynamics unfold.
Yeah, and if you're somebody who's like literally listening just for like your like equations of motion, what the hell is that?
Right.
I know your physics undergrads will understand what that means.
Yeah,
but
yeah.
It's a term used a lot to just basically mean you get the acceleration of the system,
Yep.
and you can work backwards to like position and
Yeah, because the acceleration in calculus is related to the velocity, which is related to position. So it tells you everything you need to know about how something in a system actually evolves.
right.
So like if you have a ball, if you throw a ball and you have the equations of motion, you know the acceleration of the ball, you know the velocity of the ball, you also know the position of the ball over time. So it tells you everything.
Yeah. And as you can imagine, in quantum mechanics, this gets a little strange.
Yeah.
Because talking about position and momentum, you get, there's a duality between those two, but which maybe we'll get to at some point. Like we'll cover those, how they're being handled mathematically, but.
Yeah, but the thing is, I guess just to really cap that off is
Sure.
the thing is you need to have that in quantum mechanics because that's basically what makes a theory quantum. The
Right.
fact that position and momentum cannot be measured to a complete certainty. You have to measure one or the other. It's the
Right.
whole Heisenberg uncertainty.
Yeah, and this is and there's a whole formalism, and this is why it involves quantum mechanics. Moving on to the next part that's required, you need to be familiar with that Heisenberg uncertainty. Yep. You need to be familiar with the fact that like operators, like basically how they're mathematical operations on the field in this case, right?
Right. And this is a little bit more of a higher level thing. Like it's not even obvious to me still why it gets promoted to an operator. So what they say in quantum mechanics, so for people who might just be starting quantum mechanics or those, who just are curious, you have position, right? Position would be a generalized coordinate in quantum mechanics. And then momentum would be the other. So momentum is just the mass times velocity. So for some strange reason in quantum mechanics, you use these things called Hilbert spaces to actually give the state of the system, of a quantum system. And the thing is, when you use Hilbert spaces, you have to actually promote the quantum generalized coordinates to operators. So those operators act on the Hilbert space state, the state within the Hilbert space. So if you don't know what the fuck that means, just don't
look at the math.
Yeah, don't get too bogged down into it. But for some strange reason, the position X gets promoted to an operator, and the position P gets promoted to an operator.
And you, this is more comfortable to look at when you actually see the math because you're given you deal with wave equations.
Right.
Right. And whenever we operate, these operators act on the wave functions, they're going to give you values that when they're normalized out, blah, 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 or when they kind of like, I guess, are crossed out, interfered, and, the E's and they're squared out or whatever, right?
Okay.
You get units for like position and momentum. If you can, do you remember that?
I'm not sure exactly what you're saying, but it's just basically you can think an operator acting on some state does something to that state.
Right, I'm saying, but it brings it down from when you act on the wave function. Remember how it brings down like units of stuff, like the position is EI. Do you remember that?
Yeah, I think maybe I see what you're saying.
Yeah.
I think it's a little bit detail-oriented.
Yeah.
But just
look at the math.
To keep it simple, it's just that operators are this thing that can actually operate, that can actually do something to a state.
Yeah, look at the math. It'll make you more comfortable with like, oh, that's why we use this and that's why we do that.
But honestly, even if you're trying to get this like intuitively, I don't think it's really that important.
It's really
just
not.
It's just a feature of how something becomes quantum. And unfortunately, when you try to talk about quantum mechanics, the most enlightening things you're going to get from quantum mechanics is when you're talking about the math. Mm-hmm. Because if you try to talk intuitively about quantum mechanics, that's when you get fucked, right? Because quantum mechanics and intuition don't go hand in hand, at least not classical intuition. You need a quantum intuition to talk about quantum mechanics.
Yeah. You need to be comfortable in quantum mechanics, at least. You like Terence is saying, linear algebra concepts.
Yep.
But also integration, which is you probably get it from most of your calculus classes.
Yep.
And you're going to be dealing with probably particle ensembles, which in basic quantum mechanics, you don't deal with ensembles at all. You deal with like
right, single particles and whatnot.
and stuff.
Real simple.
Yeah.
And you're talking about, in quantum field theory, you have to deal with ensembles of particles because they actually interact with one another.
Exactly, yeah. And then lastly, special relativity. With relativity, I guess there's still some crossover with general relativity. If you've taken a whole course on it, it's probably better because you're going to be dealing with like tensor stuff. Like you're going to deal with notation that is probably introduced in your relativity class.
Right. And actually, confession, I still don't understand the
Covariant bullshit. So tensors are tough.
Man,
I still don't know how to really do the math that well.
I remember understanding it, but man, it's been a long time.
Yeah, we've done it so long ago. It's like it's already out of my brain.
Yeah, it's already evaporated away.
It's the stuff that you see when it's like alphabet soup. You just see a bunch of indices everywhere.
Yeah,
that's tensor stuff.
Yeah. Oh, man, it's at the tip of my tongue. But anyway, the relativity stuff, you need to know the tensor stuff, Levi-Civita symbols, the summations over.
This is if you're trying to do the math and really get into the details.
Right.
Yeah.
So these three subjects, if you have all those three under your belt, you're ready to take on the behemoth that is quantum field theory.
Right. And intuitively, if you just know, special relativity just has to do with when things go fast.
Yeah.
So quantum field theory is basically the combination between really fast, small stuff.
Yeah.
Special relativity plus quantum mechanics.
Yeah.
And then it gets into a little bit more detail to take even further, but that's the starting place of QFT, essentially.
Yeah, it's like it's the study of sonic mechanics. I was trying to go for some funny there, but
it's a good try.
Fell flat. But I'm quantity over quality, Terence. So,
hey, they're not always going to be winners, okay?
But when they stick, you remember them, and that's what counts.
Right.
So a field. So according to this thing that I was reading, its field is spread out in space and time, and it's intrinsically wave-like. Would you agree?
Sure. Yeah.
Yeah. And it says here, applying quantum theory to the field gives physical quantities such as energy and momentum that are in QFT discretized.
Yes.
Yeah.
So the key thing about quantum field theory is instead of just quantizing, let's say like the particles, you're actually quantizing the field.
Yes.
So there's this concept called canonical quantization, which has to do with that. So the first quantization is when you're changing a classical, when you're quantizing a particle, and then the second quantization has to do with quantizing the field. So you may have heard that term, second quantization. That's a big key word in quantum field theory, and that's a part of canonical quantization.
Yeah, I remember when I first heard that in my quantum mechanics class. It was like when you're playing a video game, a fighting video game or something.
Yeah.
And it's like you see the shadow of the character that you haven't unlocked yet.
Right.
It's like that. It's like that. It's like
right. You're like, oh shit.
What is that?
Yeah.
What is that outline that I see? Second quantization.
Right. They look really badass. The outlines get all this crazy shit. You're like, oh shit, I want to learn that.
I want to unlock that. That seems super cool.
Right.
It's really on that level where the mystery, because it's like first quantization. Also cool names, by the way. Thank you, physics or physicists, whoever thought about that. It's a really cool marketing scheme. QFT says that states that have wave-like properties or have definite phases are ones that contain indefinite number of particles. So is that that's something that I guess in classical physics we don't really, that's not a notion we take on, right?
Right. We always have a conservation of particle number. In classical physics, definitely, right?
Yeah.
And then even in quantum physics, right? Because, when we're doing quantum mechanics, you're always doing systems of one particle or maybe two particles, but you never have to consider more than that, really. You don't have a collection of particles. So every time the particle has some interaction, it's always the same particle number. But in quantum field theory, that's not necessarily the case.
Yeah. And then we also deal with this the vacuum. The vacuum space or something. I don't know how to define it.
Are you talking about in quantum field theory?
Yeah.
Okay.
Like the vacuum, it's not your typical Dyson vacuum or something. This is like a different kind of energy space. It's like a
Dyson vacuum.
yeah, the vacuum is the lowest. It says, okay, I made a note here. It says the vacuum is the lowest energy state where there are no excitations that are from particles.
Right.
And that to me did not make sense the first time I read it, because I was like, what do you mean there are no excitations from particles?
Yeah.
Does that something that resonates with you immediately or no?
Yeah, I think so, but keep going.
Okay, yeah. So it says this is due to the fact that the field is approximated as an infinite collection of harmonic oscillators. So, with this concept of the Heisenberg uncertainty principle and the duality of like position and momentum, being at the lowest energy state means we still have this sort of 0-point motion.
Right.
And you can think about it in quantum mechanics. We see it in the infinite square well. The lowest energy state, you still have the nodes, or in some sense, the standing waves, I guess you could say.
Right. Because what do we have? Like in so if we have the quantum harmonic oscillator, right? We know from quantum mechanics that you get the expression E equals n plus 1/2 times h bar omega, right? And I think, can n equal 0 for that?
Yeah, that's
Okay,
the
so-
one that you can still get 1/2
Right.
h bar
but
omega.
yeah, exactly. So n equals 0. N is actually the ground state. So then when you plug in 0 into that equation, you actually still get back 1/2 h bar squared, right? So
H bar omega, I think. Or
Thank
whatever.
you, h bar
whatever.
omega. I'm sorry.
Yeah.
H bar omega. So you actually have an energy even at the ground state. So that tells you that there is no zero energy even at the ground state. And there's a similar thing in quantum field theory.
Yeah, there's a 0-point motion. That means that even at the ground state, there's still some energy.
Yeah.
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 So the particles are
Which is not really
oscillating.
intuitive, because you could think of the ground state as, there's zero energy, but it's
Well, yeah,
no, there isn't.
because classically, right, when you're at the lowest energy point,
Yeah. It's zero
the thing
energy.
is stable.
Right.
Like it's not moving.
Right.
But in the quantum system, there is still motion.
Right, because you have things like quantum fluctuations,
Yeah.
like a particle's never actually still.
Yeah. And that's kind of what that shows. And so now you promote, in this vacuum, this field now has a sort of infinite number of harmonic oscillators embedded in this field
Right.
that have this property that are in motion and have excitations.
Yes.
So,
So that shows you the vacuum is also not just a zero energy. It has some kind of energy in the vacuum as well.
yeah, yeah. Fascinating stuff. I think that's
Yeah.
kind of like the beginning. But why QFT?
Why QFT? Let's see.
Yeah, let's see.
So
All right.
I have a video of David Tong. You may recognize the name. He's basically the famous guy that has the best, or some of the best, referenced quantum field theory lectures out there. Very, very nice for people who know quantum mechanics and special relativity, who are just getting started. I mean, I really enjoyed his lectures. And then he's also got the videos online, the YouTube videos, which are not super great. They're okay. They're pretty good. They're very good, but his actual physical, lectures are really the good ones. The write-ups. But this is a video of him just talking about the history of QFT, right?
Yes. So this here says introductory remarks on quantum field theory. We'll put the videos below.
Do we need to put
sources.
the microphone next to it, or is it just going to
Nah,
automatically
it's just
record?
going to record.
Okay.
A bit of
If there's any sound.
context laid down for you. So quantum field theory started immediately after the discovery of quantum mechanics, late 1920s. These giants of quantum mechanics, people like Heisenberg and Pauli, Dirac, of course, they were all trying to quantize the electromagnetic field. Basically, for the reasons I mentioned at the beginning, they realized that had to be the correct description. By the way, the guy who first understood the way particles come from fields was probably Jordan. And he didn't win the Nobel Prize, I suspect, because he was a rather enthusiastic member of the Nazi Party. And this was, at a time way before it was fashionable to be an enthusiastic member of the Nazi Party. So these guys sort of laid the foundations of quantum field theory. Late 20s, all the way through the 30s, were trying to understand the way to quantize a field. And they basically failed because of this infinity, because they couldn't really make sense of having a theory with an infinite number of degrees of freedom. So if you look, there are these very interesting quotes from people like Dirac at the end of the 1930s saying, I think we've all now decided to junk quantum electrodynamics. Thank God we never have to go back and look at that again. It's an ugly theory. So that was basically the situation leading into the Second World War, was that people had tried and laid down the framework for quantum field theory, but not really managed to succeed to make sense of these infinities that arise. I should say, what we're going to do in this course doesn't go a lot beyond what those people did in the 1930s. It's really just the very basics. We're kind of going to take a route which just avoids mentioning these infinities whenever possible. Okay, so then the next big success came after the war. It was the new breed of physicists, Tominaga, Schwinger, Feynman, Dyson. And they understood how to make sense of these infinities through a process that they called renormalization. They developed the theory of QED. It was phenomenally accurate. There'd never been a theory like it, which agreed with experiment to such incredible number of significant figures. But even then, I think there was this underlying suspicion about what they were doing. This idea of renormalization to get rid of some infinities. You read statements that it was like sweeping infinities under a rug, that Feynman called it a dippy process. People were uncomfortable with this. So by the 1960s, it was really falling out of fashion. People were discovering new particles all the time, mesons and baryons, and strong resonances. And somehow the idea you should have a field for each of these was a little bit upsetting to people. And so other techniques were being developed. Techniques sort of a little like what you were suggesting. You junk the classical field and you go to something more abstract. In that case, it was the S-matrix or bootstrap methods or things like this. And I think in that time, in the 60s, there were probably only a handful of people working on quantum field theory. And then we get to the 1970s, and this is the golden age. Asymptotic freedom tells us that really it's a quantum field theory that's built underneath the strong force and gives rise to all these dozens, hundreds of particles that were seen. These infinities that are there from the beginning, they're finally understood in a deep and profound way, starting with work by Kadanoff, by Wilson. And this really gives rise to I think, the most important part of quantum field theory is understanding these infinities using what's called the renormalization group. Meanwhile, there's progress on understanding the way geometry and topology fits into quantum field theory. And I think from then, it's been clear that it's the framework in which nature is written, certainly on the energy scales that we've probed so far. Okay.
So David mentioned some interesting things in there. One of them being, he was saying that quantum field theory was basically started development directly after quantum mechanics, which I didn't even realize. So Dirac started working on that in the late 1920s. So you think of like this really sophisticated theory and all this stuff to happen way later, but they actually started it around the same time as like quantum mechanics was finishing up, which is kind of weird. But it actually makes sense, right? Because it's in the vein of quantum mechanics, but it just was unexpected for me to learn that. Because I guess Dirac was just trying to, he realized that to complete off quantum mechanics, you need to actually have it aligned with, you have to have it compatible with special relativity. And quantum mechanics, as we know, is a non-relativistic, massive, or theory for massive particles, right?
Massless particles.
No, massive.
Oh, sorry,
Yeah, quantum mechanics. Yeah.
Yes.
So they needed a special relativistic quantum theory, for it to be complete. But I guess quantum mechanics is complete, and then quantum field theory was the answer to the relativistic portion of quantum mechanics.
Yeah. And QFT is technically the study of elementary particles, right? and their interactions. Like elementary particles are massless. Like they're endued with this like with the Higgs mechanism. You know what I mean?
Maybe so. I didn't get that far to say that, so I can't really corroborate you on that.
Okay, well, I'm quoting a source here. So
Okay.
a physicist. So I'll put if you want to check these out. It's very very short books. There's quantum. I think it's quantum. Very short introduction to quantum theory, and then there's the other one with like I forget the name, but it's a really good book. Anyway, check those out in the comments below.
Well, David Tong also gives a lot of good book recommendations during that lecture.
Nice.
So if you guys want to go back on YouTube, maybe I can even link it in here. David Tong has that first video that he has on his lectures is really good. A really good comprehensive video on quantum field theory, and it's about an hour long. He doesn't do any math, so it's all conceptual.
Yeah. And one of the crowning achievements of QFT, like it's very successful. It's like the measure of the electron's anomalous magnetic dipole moment. It's like 10 to the -8 or something,
right.
Decimal points or something.
Not 10 to the -8, but you're saying like 12 decimal points or something.
It's like like the accuracy is like 8 at least, right?
I see, yeah. Something
like
crazy like that.
Something absurd.
Right. It's one of the most successful theories ever devised.
Yeah.
Which is why people had to keep it around.
Yeah.
They're like, well, this shit does work very well, so.
Yeah. I mean, that's kind of why they were saying about the renormalization stuff. It's like, they're like, well, it's magic. I don't got to explain shit. It's like,
right. That's another thing I wanted to kind of address. David Tong mentioned the renormalization, and then there's another stronger thing called the renormalization group, which people talk about. I didn't really get too far into that because it was actually kind of complicated. But I did find a nice little paper that started talking about the renormalization group from a perspective of someone who doesn't know quantum field theory.
Yeah.
And I put it on Twitter. But it's interesting because I found a lot of stuff where the renormalization was used in other fields as well. Like a lot of other fields, like AI, it was used in, I think, of course, condensed matter uses renormalization, which is me and Juan's field. And then there were some other fields that use renormalization. So it's really, it seems it's really transcended just physics and it's gone to a lot of different other fields.
Right.
So it seems like people have really cracked what renormalization means. But I guess long story short, renormalization is the way that they were able to sweep these infinities under the rug, as they say. Because one of the big problems with quantum field theory initially was they couldn't figure out a way how to solve these divergences in the theory. So things were blowing up and they were not matching reality. One of those being the vacuum state energy. I think it was blowing up to infinity. So when they introduced renormalization, Tominaga, as Tong mentioned, in around the same time as Schwinger developed renormalization in order to fix this. So it's this really powerful concept. Another one of these unlockable characters. That's probably it's really deep, and you could probably explore a lot about it to understand it. But I don't think we're going to go into it too heavy this video. But just know what it is.
Yeah. It also helped us like understand like 3 out of the 4 fundamental forces. You know.
Renormalization did.
Like no, I'm sorry, QFT.
Right.
Like
because this goes into the Yang-Mills actually.
Yeah.
So, or I guess I don't know if this is necessarily Yang-Mills. I think it is, but I didn't really get to connect Yang-Mills to quantum field theory. Gotcha. But I think Yang-Mills is considered a quantum field theory, and Yang-Mills has to do with talking about the electromagnetic force and then the electroweak force, I should say, and then the strong force and the
electromagnetic interactions.
Yeah. So I guess the strong force and the electroweak force, I guess, is what you would say.
Yeah.
And then, of course, the final force that's kind of the mysterious one is the gravity that we still haven't figured out how to actually put together.
Which is why we can't build UFOs, man.
I know.
No, I'm just kidding. Once we unlock that, we'll be ready for space flight. We'll be ready to get off this planet.
Right.
Yeah, and I mean, QFT is responsible for describing the Higgs mechanism. Like Higgs famously, he got his Nobel Prize in it. He was able to discover the Higgs particle using QFT, and it's one of the crowning modern achievements, I would say.
I didn't even know that.
Yeah. Helps explain why all electrons have the same properties, like are indistinguishable according to this.
Right.
Yeah.
Well, that's one of the big things of why QFT, I guess we should have mentioned.
Mm-hmm.
So some people might be saying, why do we even need to develop QFT?
Yeah.
And we mentioned a little bit earlier, there was the whole thing of conserved particle number.
Mm-hmm.
Well, as you know from, I'm sure you've seen it, David Tong uses this example. If you look up the RIC accelerator, this is the RHIC accelerator in Brookhaven National Laboratory, you see this picture of this like star-looking thing, and that's all of the particles that basically explode out of these collisions that they do in these, accelerators.
Sure.
So the higher energy you get, the more particles you can actually get that come out, because as we know from Einstein's relation, E equals mc squared, it shows there's a mass energy equivalence. So then as you ramp that energy up, you actually can get more and more particles. So it just shows you that particle number is not necessarily conserved when you have special relativity combined with quantum mechanics.
Mm-hmm.
So you needed some kind of theory that would take an account of this non-conserved quantity of particles. And then, as Juan mentioned just now, was the whole indistinguishability of particles. So particles can be interchanged, and every electron is the same as every other electron. Every proton is the same as every other proton. So they were trying to look for a way to explain that. And the way they came up with it with QFT was there's this underlying field. So every electron has this is a part of an electron field, and then the way that they manifest as particles is just by these excitations, to where you actually create a particle from this electron field, and then that happens for every other particle as well.
Yeah.
So they quantize the field in that sense, that you get these you have this quantized field, and that actually creates these particles, as the field
Is
exists.
excited. Yeah.
Yeah.
Yeah. Yeah. Well, that's neat.
Yeah.
It's cool stuff. Whoever came up with this was definitely on something, I will say. No, but
Well, you just gotta follow the math.
yeah, that's true. But QFT is also able to explain some more like modern. I mean, this is really the crowning achievement of modern physics, like the crowning jewel.
Yeah, people would definitely consider this as like one of the most elegant theories ever devised, or at least one of the most predictive / corroborating theories for experimentally.
Yeah, that we currently have.
Yeah.
You really haven't gone into modern physics until you really did
Gone to
do QFT. Yeah.
I regret I didn't do it.
Yeah, me either. Well, I did an aspect of it, but even then, it's very limited.
Yeah.
Because like for condensed matter people, you're gonna see QFT in like explaining the fractional quantum Hall effect, and even superconductivity. Like you're gonna see it in aspects of this.
Where does the renormalization come in QFT? Do you remember?
In
Condensed matter stuff.
condensed matter,
Yeah, many body.
It's still treated in a way where you use Feynman diagrams to really make sense of all the infinities and stuff, and like kind of rule out which ones you just completely disregard don't contribute to your calculation. And the ones that do contribute to your calculations are the ones that are obviously finite and they converge. So the Feynman diagrams, the Feynman rules are a huge aspect of this, and using these techniques to give you finite results.
Gotcha.
So yeah, I guess onto the math. I guess right from here, like
yeah, let's do it. So now I guess we're gonna go into like how people do QFT. So I really wanted to not just make this a general, a general talky podcast. I mean, it is still, but I want to actually like get people some kind of understanding of what actually the hell is QFT when you do it mathematically. So, this is the Tobias Osborne one.
Yes.
This is a conceptual one. Maybe we should skip this and go to this one, because Tobias Osborne has really great videos on QFT. I suggest you guys check out his lectures as well. But I think we're just going to skip that for this podcast, and let's move on to the Zap Physics, how to visualize quantum fields. So let me give you an introduction, I guess. So the thing about with QFT is we talk about quantizing the field.
Yeah.
So you start with this classical field and you quantize it using canonical quantization, second quantization for quantizing the field, they say. And what this guy, Zap Physics, is showing you is how this first video is going to be the classical harmonic oscillator, basically. And then he's going to show you the difference between the classical harmonic oscillator and the quantum harmonic oscillator. But then you might be asking, some people might be asking, that's quantum mechanics. What does that have to do with QFT? Well, the thing is, a field in QFT is modeled as a lattice of quantum harmonic oscillators, basically. So it's just like quantum mechanics in that sense, in some weird ways, where now it's just imagine the field is a bunch of quantum harmonic oscillators. So at every point there's these particles, and they have these quantized states in the field. So yeah, but he makes a really simplified version here, and he just puts them in a ring so you can clearly see the pattern. So we're going to start off with the classical harmonic oscillator real quick, and then we'll move on to the quantum.
Cool.
In these simulations, the springs which are compressed will be red, and the springs which are extended will be blue. The more compressed, the more red, and the more extended, the more blue. When the springs are relaxed, they'll be gray. Okay, let's see what happens. When we start with a small number of masses, there aren't a whole lot of patterns to see. Once we release the mass, everything just starts oscillating back and forth in a messy way. However, we can immediately see something interesting. It looks like it takes some time for these oscillations to actually reach the other end of the ring. In other words, it looks like there's some maximum speed that the forces can travel through this ring.
So they're increasing the number of nodes.
Yeah.
So just got this ring.
When we get
It's
above
increasing
about
those.
100 masses, I'll make a few changes due to the fact that it gets very hard to see what's going on with individual masses and springs. First, instead of drawing all the springs and masses, I'll only show the colors of the compressed or extended springs. Second, instead of starting out by displacing only a single mass, we'll start by compressing all of the springs in a certain region and extending all of the springs in the other. This makes more sense to do anyway, since our end goal is to describe the continuous string, and it doesn't really make sense to displace a single piece of a continuous object. So for about 100 masses, nothing's really too much different from the cases with fewer masses. However, watch what happens when we increase to 500 masses. It looks like two copies of the initial compression and tension regions start to zoom around the circle in opposite directions, while everything else seems somewhat stationary. But it isn't perfect, so they start to develop tails of oscillating masses in their wakes. When we increase the number of masses even more, these tails take longer to develop and stay smaller than the case of 500 masses. By 5,000, the tails almost don't even show up at all. This pattern of course continues until we have a true continuum, in which case we don't develop the tails at all, and we just get these two copies of the initial state moving around the ring at a set speed. So already we see how something which looks sort of particle-like could arise from a field theory. If we start with pieces of our field in a certain state, these pieces will keep their form and move around like we might expect a particle to. However, these aren't truly particles. They're really just regions of high and low density in the string. In other words, these are sound waves which propagate around the string. But we aren't done. There's nothing quantum about this field theory. So how do we upgrade this classical string to a quantum field theory?
All right.
Well, it's easy. Instead of using
So then he just demonstrated what the classical version of that is.
Yeah.
But it's not quantum, right?
So next he's going to show the quantum. So you can go to the next video one and just skip a little bit to the quantum one. It's
Well, it's already there. I skipped to it.
Gotcha.
But the one that's really important here is that the quantum oscillator can't have any energy that we want. In fact, the energy can only come in integer multiples of a constant determined by the properties of the oscillator. In essence, the energy of a quantum harmonic oscillator comes in chunks, and every oscillator can have only a whole number of these chunks of energy in it. So let's set up our system in the same way as the classical system. Just take a ring of quantum harmonic oscillators and start increasing the number of them to see what happens. We'll prepare the state so that there's a single chunk of energy in a single oscillator. Now, these oscillators can still interact and pass this chunk of energy between each other. However, due to the nature of quantum mechanics, after we start the system running, we can't exactly say where this chunk of energy is. We can only determine the probability of finding this piece of energy in each particular oscillator. I'll represent this by how red each oscillator is. The more red, the higher the probability of finding the unit of energy in that oscillator. Okay, let's look at how this works. Like in the classical case, when the number of oscillators is small, things look pretty random. Now, like we saw in the classical case, around n equals 500 we see a big change. We get two main regions where the probability is highest, which propagate around the circle. However, after a while, we again see the probabilities start to smear out over the full ring. As we increase the number of oscillators even more, this high probability region gets even smaller and holds together for longer. When we reach n equals 5,000, we really start to see how we can get particles from this theory. The two very red regions are very small and also quite stable. For the entirety of the simulation, we don't see these regions smear out nearly as much as we did for the case of fewer oscillators. As we might expect, when we take n to infinity, the non-zero probabilities are localized in 2 points which travel at a fixed speed around the ring. As it turns out, the speed is exactly the speed of sound we found in the classical case. So it seems that instead of having sound waves like in the classical case, we have sound particles, called phonons, in the quantum theory. The two parts just come from the fact that there's a 50% chance that the phonon is traveling clockwise and a 50% chance that it is traveling counterclockwise. So why do we consider these actual particles, whereas in the classical theory we did not? Well, remember in the quantum case, we have to have discrete units of energy in specific oscillators. In the case that we only have a single unit of energy in the system, there's no other option than to have it localized at a single site, even though multiple oscillators may have some probability to be the home of this unit of energy. In this sense, each unit of energy behaves...
So you see what happened there is basically he showed how you can start with this quantized field, and you can end up with these particles, basically, just like in quantum field theory. You have a quantized field, and then you can actually arise, particles in a system. He just created this closed version of a quantum harmonic oscillator loop,
Yeah.
Whereas really it would be all space would contain these particles, but that's basically basically the way to visualize quantum field theory in some sense.
Yeah, it's kind of intriguing because the phonons, or getting phonons, is probably the real sort of analogy, a real good analogy to the quantum field, because you get phonons naturally in condensed matter. They kind of arise because in crystals you have a lattice of atoms and stuff, and the phonons naturally come out of the math.
Because basically the condensed matter version is just it's the quantum of sound, right? It's a lattice quantization. But instead of like a physical lattice in quantum field theory, you can just think of the quantum field of whatever the particle you're using is. So it's not a phonon necessarily, but it's the same physics, right?
Yeah.
The real one is a phonon, but this one is actually like a photon or whatever, or electron or whatever.
Yeah. It explains like a lot of these quasi particles. You'll hear that a lot when you get into higher level physics. The arise or just sort of these quasi particles coming out, like phonons, like other phenomena. Like I'm trying to remember other names, but I'm blanking on them.
Yeah, I forget too now.
But there's so many. There's like a zoo of particles, like quasi particles that kind of come out depending on like the boundary conditions of the system in some sense. So
anyway,
we also have a couple other. There's what how would you explain this?
Yeah, so this next video is actually the one that's going to go into the math. So hopefully this is understandable, especially for audio listeners. But he goes into in a very conceptual way, still using the math. So he doesn't go into heavy detail, but he tells you all the steps. So this is actually how you would solve the free scalar field, basically. So there's an equation called the Klein-Gordon equation. And people thought that was the way you could try to quantize or try to combine special relativity and quantum mechanics initially, but it wasn't the right way to do it. But then we later found out from quantum field theory that was actually a special case for just the bosons. So this is like the way you start off with quantum field theory. So if you want to get started in quantum field theory, the way you do it is to quantize the free scalar field, essentially. And this is a video that kind of steps you through the mathematics on how that's done.
Yeah, first off, I want to say this
These
video.
next two, sorry.
Yes, I was going to say this video looks like, I don't know, I see IOP engineering physics. It looks like this. Is it an animation or is this guy like
No, this is
in
a
a closet somewhere?
He's like in a closet.
Free this poor man. Free Badis Yidri. He's trapped. They're forcing him to do physics, but anyway, we'll play it. Here we go.
Quantization of the free scalar field. The starting point is the Klein-Gordon equation. So this is the usual equation for a scalar particle. A scalar particle means spin zero particle. So m is the mass of the particle. Now, now we are interested in canonical quantization of phi x is the field, is the scalar field. So it is the dynamical variable. That's what will play the role of the generalized coordinates. Now, the starting point of canonical quantization is the Lagrangian density, Lagrangian formulations. We therefore need to write down a Lagrangian density. The Lagrangian density will be a functional in phi and mu phi, which are the derivative of the field. So from the Lagrangian density, I need to define the Lagrangian, which is simply the integral over space of the Lagrangian density. Then I define the action, which is the integral over time of the Lagrangian. Now, after that, the usual Hamiltonian principles of least action. The Hamilton's principle of least action states that the minima of the action, the saddle point of the action, are given by the classical solutions. So the classical solutions, phi CL, so the classical solutions, the classical configuration of the field are actually minima of the action. They need to minimize the action, or in general, they are extrema of the action, so they need to extremize the action. So this equation here is in fact Euler-Lagrange equation of motion. So that means we can simply verify this. We can simply prove that this principle, Hamilton's principle of least action, gives us exactly Euler-Lagrange equation of motion for the field phi, for the dynamical variable phi. We want this equation to be the Klein-Gordon equation we have started with. We find the solution, which find the expression for the Lagrangian density given by 1/2 d mu phi minus 1/2 m squared phi squared. I leave you as an exercise to verify this fact, that the equation of motion which derive from this Lagrangian density are precisely the Klein-Gordon equations. Now, the second step, after we have written down the Lagrangian density, so we need to derive the conjugate field associated with the scalar field. So phi will play the role of q, the generalized coordinates. We need to find the conjugate field pi, which play the role of the conjugate momentum, the canonical momentum. This is the derivative of the Lagrangian with respect to the velocity, which means the time derivative of the field. The time derivative of the field is effectively the velocity. So p here, the field pi here, we can show that it is simply dt phi. Now, the Hamiltonian is the Legendre transform. This is known. So we do the Legendre transform, we get this expression. Then this is actually what we have found here is the Lagrangian density. Then we find the Hamiltonian by integrating the the Hamiltonian density over space. So we do this. In order to do this, we need an expression of the field phi. The most general solution of the Klein-Gordon equation is given in this equation. This is a crucial equation. This is the most general solutions. So we integrate over all values of the momenta. Now we have here the positive energy solution, and you have here the negative energy solutions. They are multiplied by general coefficients. A p and A minus p star are general coefficients. We have also plane wave. This is plane wave multiplied by this phase, that is an incoming, and multiplies by this phase, that is an outgoing. This expression needs to be evaluated at p0 equal EP, which means that it needs to be evaluated on shell. So this is the most general solution of the Klein-Gordon equation. Now, using this solution in the Hamiltonian, so we go back to the expression for the Hamiltonian, which means this line, and simply substitute the field and do the integral. This is quite a long calculation. The end result is the following Hamiltonian for the scalar field. So this is the Hamiltonian of the scalar field. So it's 1/2 P, that's the energy of a single mode P, multiplied by this number, which as we'll show now, it turns out the number of modes. Now when we quantize the system, this will be clear. This is the number of modes which have momentum P. Now the other ingredient. So we get the expression. This expression, as I said, which is the integral of momenta of 1/2 EP. EP is the energy of a single mode P, whereas this number, as I said, is the number of modes, as we will show this, is the number of modes with the momentum P. The last ingredient we need is a Poisson bracket, which is the basic structure inherited from Lagrangian mechanics. So this is basic structure essentially in Hamiltonian mechanics. So phi pi at equal time Poisson bracket is delta Dirac. Now, quantization means introduction of a Hamiltonian, introduction of a Hilbert space H. So phi, the field will become an operator, the momentum becomes an operator, the Poisson bracket is replaced by 1/E, the commutator. So we get the fundamental commutation relations, equal time commutation relations, phi hat Tx, pi hat Ty is I delta Dirac. Now, the field becomes an operator, so therefore the coefficients A and A star becomes operators A hat P, A dagger, A hat dagger minus P's. These are operators which are also acting in the same Hilbert space. We can show from the fundamental commutation relations that these operators need to satisfy these commutation relations, which reminds us which is reminiscent of the quantum harmonic oscillators. In fact, we have an infinite number of them, of quantum harmonic oscillators, which are decoupled. We have an infinite number of decoupled harmonic oscillators. This is really what we have. The system here, the scalar field, is really equivalent to this system. An infinite number of decoupled harmonic oscillators. The Hamiltonian operators, so the Hamiltonian also becomes an operator, and the order now, this is dagger and this dagger, so we can check that this Hamiltonian commutator with A dagger is an energy times A dagger, commutator with A is a minus energy A. This shows explicitly that A dagger is a creation operator of a mode with the momentum P, whereas AP is an annihilation operator with the momentum P. This is direct. Now, the last point.
So yeah, that's good. So that guy pretty much gave a really nice, quick summary of the whole way to solve the basic free scalar field of quantum field theory.
Yeah.
So did you have anything that stood out there, Juan, to you that you had any questions about?
Mostly about the expediency at which he approached this.
Oh, it's a little too fast, you think?
No, I mean, I think for me it makes sense because I've already seen a lot of this.
Yeah, okay.
But for the poor undergrads who
For the undergrads, it may be a bit tough, but I guess the key things to take away would be you have the generalized coordinates in quantum mechanics. We think of it as x for a position, p is momentum. X gets changed to the field, phi, and then P gets changed to pi, which is basically the conjugate momentum of the field. He basically goes through solving the classical field theory, essentially. And then once he solves the classical field theory, you can make a Poisson bracket relation between phi, the field, and pi. And then also, of course, you get the phi from that and pi from that. And you can solve for those Poisson brackets to give you the Poisson bracket relationship, which gives you some kind of Dirac delta function. Then what you can do is to quantize it through canonical quantization. You promote phi to an operator, and then you promote pi to an operator, and then you can also promote the Fourier coefficients A and A dagger, which were in his his phi expression, the integral. You can promote those into operators, and you can actually then promote the Poisson brackets of phi and pi to the commutator, which gives you a new Dirac delta expression. And then you can also get a commutator from those two Fourier coefficients if you find the Hamiltonian from that. So he's basically showing you how to quantize that whole classical field. And the key thing of quantizing something is to basically change those generalized coordinates to operators, phi and pi, and then to also have that commutator relation, phi and pi's commutator. Just like in quantum mechanics, we have x and p's commutator, which would normally be IH bar, right? In this case, though, it's going to be some kind of I Dirac delta function. So he's basically showing you that the system is quantized. And then, as of course, also what you know from solving the harmonic oscillator in quantum mechanics, you get these creation and annihilation operators. And then he explicitly shows that you can get those creation and annihilation operators as well from the Hamiltonian in the expression. So that's it. So it's just basically showing you how to quantize that free scalar field, essentially, from the Klein-Gordon equation.
Wow.
Yeah. It's a lot to take in, but it's like the actual, it's a great way, I think, to start off, the simplest way to start off with quantum field theory. Of course, if you don't understand that, don't feel too bad. You kind of have to know quantum mechanics really well. You know, me and Juan are really comfortable with quantum mechanics. If you just know how to solve the Schrodinger equation with quantum mechanics, it's all you do. You'll get really familiar with it.
Yeah.
And then this stuff really translates nice and easily to your understanding.
You also need to know like the utility in using commutators and commutators and
anti-commutator. Poisson brackets, the anti-commutator.
Yeah.
That's the classical version.
Right.
But the reason for the commutator is Heisenberg's uncertainty.
Yes.
They needed to create this kind of mathematical object to show you that
order matters.
X times P is not equal to P minus X.
Yeah.
Yeah, order matters because these two things are now, they have this Heisenberg uncertainty relation where they get promoted to operators. It messes up normal multiplication where X times P is not equal to P times X, which is P is momentum, X is position. So you get that, you see Heisenberg's uncertainty principle, which says delta X times delta P is greater than or equal to H bar, like over 2 or something.
Yeah, you don't get zero, essentially.
Yeah, you don't get zero. So the commutator shows you that you won't get zero. So it's a mathematical object to keep in that Heisenberg uncertainty.
Yeah, and that's deeper than most people think because there's a good analogy of like it's like when we read, right, in English, I guess, the order matters.
Right.
Like left to right.
I don't know if this is a great analogy.
Well,
but
you read left to right. It matters. Like it's gonna make. That's how you make sense of it.
Okay, I see what you mean.
Reading right to left, you're gonna be like, I don't understand what this is.
Yeah,
you're gonna get something incomprehensible. It's
right. And it's something you take for granted because when you multiply two numbers, 3 times 2 is always the same as 2 times 3. It's only when you start to get into matrices and things that's not always the case. Mm-hmm. Matrix A times matrix B does not necessarily equal B matrix times A matrix.
Exactly, yeah.
So the order does matter, and that's a critical thing in quantum mechanics. That's how you know that the system is quantized.
Yeah,
because if those two things do commute, let's say, that means that means that X times P minus P times X equals 0. Then that's not a quantum theory. that means you have not quantized anything. So this commutator relation is one of the critical components to making something quantized.
Because in Poisson brackets, like the classical systems, like typically those things are additive, right? It's like easy to see in classical systems, right?
Yeah.
Yeah.
So the anti-commutator is just the plus version of the
plus
commutator.
version, exactly. Yeah.
And I think that actually is what you use in the Dirac field quantization. Mm-hmm. But we're not going to get into that. That's the one that's to do with like spin.
Yeah.
But it's a little bit out of the scope for this podcast, so I'm not going to get into it. But that's like a more realistic version of a field. This one's kind of the toy model version that works just for like bosons, but it's very simple and elegant. It's a great way to start off with quantum field theory, which is why I chose to show that.
Yeah.
And we can show the next video. It's basically the same thing. Mm-hmm. This is Dietterich Labs, except it's just another time. I just like to do things kind of multiple times so you can really understand it. Mm-hmm. And this is basically just another version of quantizing the free scalar field by Dietterich. And he goes into even more detail because he actually solves like all of the important aspects. But we can stop whenever it feels kind of comfortable.
Cool.
Here we have the Lagrangian density of a real scalar field. From this we can see that the equations of motion are simply the Klein-Gordon equation right here. Of course, all these calculations will be done in natural units, as you've probably already noticed. Now, for a bit of a notational thing, if we take k dot x to be the four-dimensional dot product, we can construct a general solution to the Klein-Gordon equation out of plane waves if we take omega, which is the time component of the momentum, to equal this value in terms of the mass of the Klein-Gordon field and the mechanical momentum associated with the plane wave. If this relation is satisfied, then these phase factors there solve the Klein-Gordon equation. So we can construct a general solution to this equation by taking an arbitrary linear combination of those plane waves. Now, if we take the sum of this term and its complex conjugate, the field actually is a real scalar field, because then it is equal to its own complex conjugate. Or, in other words, just make sure the Fourier coefficient on this other phase factor is the Hermitian conjugate of this value here. And I say Hermitian conjugate because these are going to become operators. But before quantization has been performed, well, these are still just normal numbers. The dagger just corresponds to complex conjugation. Also, this integration measure here is in fact Lorentz invariant. Now we can calculate the conjugate field to phi, and simply plugging in the value of the Lagrangian from up here into this formula for the conjugate, we get that the conjugate is just phi dot. So then applying the time derivative to this formula for the field here, we have a formula for the conjugate field in terms of the same Fourier coefficients and phase factors. So now let's quantize. In quantum mechanics, we're familiar with the commutation relation between the position and the momentum, and here we're generalizing that to the field and its conjugate. We also remember that the position operator commutes with itself in quantum mechanics, and we remember that the momentum operator commutes with itself in quantum mechanics. And so then we generalize those to the fields commuting with themselves. So these are the generalized canonical equal time commutation relations because they're evaluated for the same value of time. These canonical commutation relations will be used to quantize the theory. In order to satisfy the first commutation relation, phi and pi must be taken to be operators instead of numbers. This can only be the case if the Fourier coefficients a of k and a dagger of k in the above expressions for phi and pi are taken to be operators that satisfy particular commutation relations. And the reason why that's the case is because everything else in these formulas we can see are definitely just numbers. So we have to ascribe the operator character to these Fourier coefficients. The above commutation relations and expressions for phi and pi can be used to deduce commutation relations for a and a dagger that are consistent with the commutation relations we've already written down for phi and pi. So the basic idea here is that we look back up at these expressions for phi and pi in terms of A and A dagger, and we invert these relations. And then what that will yield is relations that give A and K in terms of phi and pi, and we can just directly commute them, which will ultimately result in us having to evaluate commutators of phi and pi, but we've already figured out what those have to equal to give a properly quantized theory through an analogy to quantum mechanics. And of course this gives the physically correct answer, so those analogies are valid. The first step to inverting these relations is to basically take an inverse Fourier transform of this phi field and then later the pi field. And what that gives us is this value here, because this exponential goes through, and the exponents from this exponential and the exponential in the formula for phi simply add. That's where this comes from. Then the next thing we can do is we can set this up for easy evaluation of the integral over x. So if we split up these contracted 4 vectors in the exponent and then split up the exponent into a factor of 2 exponentials, then we arrive here. The reason why this is beneficial is because we know these formulas for the delta functions. So then substituting those in, we arrive here at this formula where these exponentials here and here have been integrated over to yield those delta functions. However, this enables us to do the k integration really easily because it's simply a delta function. And then we arrive at this formula for this particular integral of the phi field. Now that the integration over k is done, there is no reason to keep the prime marker on the other momentum variable. So the final answer is just this. Now the same calculation can be done for pi. So we have that same integral here, except we put pi in there. And then we follow the same procedure. We stick the value of the pi field in, we multiply the exponential through, the exponents add, and then we split up the exponents to get ready for the integral that will yield delta functions, the integral over d cubed x. We apply these formulas for those integrals again, and we arrive here. This allows us to do the k integration, and that yields this formula with no integrals in it anymore. So then we have this result. With these two relations, it's now easy to see how to write a of k and a dagger of k in terms of phi and pi. One can see immediately that these formulas do in fact give a of k and a dagger of k. The a of k and a dagger of k operators are called harmonic oscillator raising and lowering operators because of their very similar properties to those in the famous harmonic oscillator Schrödinger equation problem. As we explore the properties of these operators, we'll see that they really do behave just like that. It's not immediately apparent because we haven't explored it deeply enough, but you'll find that in fact the statement here is absolutely true as we characterize these operators more and more. So now that we have the formulas for these a of k and a dagger of k in terms of the pi and phi fields whose commutation relations we know, we can, as per our plans, commute them. Now the first one is the most interesting one, where we commute a of k and a dagger, and what we can do is we can simply plug in the formulas we've just got for the a of k and a dagger of k. We simply get this, and then start trying to simplify it. So the first thing we notice is that the phi's and pi's commute with each other, so that immediately gets rid of a lot of things. Some things cancel, and we arrive at this formula here. And then we remember that the commutator of phi and pi gives you this delta function here. So inserting that value for the commutator here, we find that we're able to do one of the x integrals, and that the result is simply this. So then if we split this up again, we find another delta function in here. So putting that in, we finally find the result for the commutator. So here is this really important result for the properties of these a and a dagger operators. One can also show that a of k and a dagger of k commute.
That is like a beautiful result here.
Right.
Like we use that at least in the how would you say, the condensed matter.
Oh, you've seen this one.
Yeah.
Okay.
This is we cover this in like the first couple weeks.
Yeah.
This is important formalism to know, like, because
Yeah, go ahead.
no, just because it's you're gonna deal with in these systems just having to know or using the raising and lowering operators on like the vacuum or whatever on this like the fields.
Right. The
Yeah.
raising and lowering operators are really nice because they have this really nice property of helping you just find the next state up in energy level. So it's like this real easy way to just plug in a number and get the the next energy level up, which is why they do this. So Dietterich Labs gave this really nice, I guess, part 2 to the other video we just looked at to actually show you the commutation relation between the Fourier coefficients of the raising and lowering operators, basically, and how they give you that that result from that. So yes, and he goes on and on. He basically does a whole comprehensive. We don't have to look at it; it's kind of long.
No,
but
yeah.
He goes through a whole comprehensive
Walkthrough.
of that free real scalar field. So if you guys are interested in that, just look up Dietterich Labs and look at his first video in the quantum field theory series.
Yeah, it's good. It's very important. Like that is, you need a good foundation of that. And if you want to, I guess, study in more detail, if you're taking like a sort of QFT for condensed matter, there's probably a lot more resources for QFT online.
There are actually a lot of QFT stuff. People love QFT, it seems.
Yeah.
I'm like, damn, there wasn't this many resources from some of the other class I took. Like special relativity was kind of barren, or GR was not that much.
Not much.
QFT's got a bunch of shit out there. And a lot of videos and stuff. I guess it's because it's like the real sexy physics right now, you know?
It's a unicorn
Yeah.
physics. It's like, oh, this is it's like in that video game where you like in a video game where you get the rare item or something.
So everybody wants the rare item.
It's the biggest thing.
But yeah.
It's what was like the most surprising takeaway from this for you?
I guess for me, it just wasn't obvious that you needed to quantize a field. I never understood why fields had to be quantized. And it really just spills out from the math, I guess. And then, you know, and we didn't get to like the Dirac equation and whatnot, but, you know, he shows how spin comes out from finding, you know, the special relativistic formula combining quantum mechanics. And also another video, we didn't get to see how to derive the Klein-Gordon equation. Andrew Dodson does a really good video on that if you want to go look that up.
Shout out.
But yeah, it's interesting. I didn't really expect, I didn't understand, it was not a naturally intuitive thing for me to see a field be quantized, to progress in physics past quantum mechanics. I never even thought about that as being a thing that had to be done.
Yeah, those relations are so powerful because when you get to the nitty-gritty of it, those Dirac delta functions, and I know that mathematicians hate the Dirac delta function.
Right, I guess it's not rigorous.
It's not really a function, but whatever.
Oh, yeah. Distribution then. Dirac delta distribution, how about that?
But what it really says is that you get a definite value. It's almost like a constraint. It's a condition that physicists use. It's like we know the particle's there.
Yeah.
So we're saying that it exists there.
Yeah.
At that energy, at that momentum or whatever, at that K value.
Right.
When they're equal, you know, it's because fundamentally we're dealing with waves, right? They either add together or cancel, right?
Sure.
Right? So they either like combine or they destroy and they interfere, I guess. And it makes a lot of the math easy. It makes a lot of like
some of it only
the commutation,
possible, right?
Yeah. The commutation relations are powerful in that way.
Yeah.
You saw what this gentleman did, and he was able to throw away a lot of extraneous terms that just kind of didn't contribute to the calculation.
Right.
And yeah, just powerful stuff.
Yeah.
Yeah.
What was one of the things you found most shocking about the theory? Or was that it?
Just I mean, how powerful it wasn't until that class that I really kind of had an appreciation for the commutation relations. Because in like general quantum mechanics, we only really see them to highlight like the incompatibility between momentum and position.
Don't say incompatibility.
Well, like in sort of like the using them as operators.
Yeah, showing that one has a dependency on the other in some sense.
Yeah.
But it's critical. You need that for quantum theories. You have to have something that's a non-zero commutation relation between the two. You know, the conjugate momentum and the position.
Yeah. Fascinating
So there you
stuff.
Interesting. Any final comments, Juan? I think we're
Yeah, I think we're
passing the
definitely
time.
gonna have to do another one.
Yeah, and also I guess for the audience, guys, was that understandable at all? Especially for the audio listeners, if possible, if you guys can leave a comment. Was that understandable? I know it's a lot to take in, but it's one of these behemoth theories, right? It's basically you're basically now on the forefront of modern physics.
Yep.
This is where it's at, basically. And this is in the realm of all the theories of everything shit. So this is it.
Yeah.
So just make a comment. Did it make sense? Did you guys like it? Do you want some more? What are you interested in seeing? All that kind of stuff. Leave a comment.
Yeah, leave a comment. Maybe we'll do a lecture series kind of in the vein of what's some of the other video lectures we've done. Kind of.
Have we done video lectures?
With guests?
I don't think we have.
With guests.
Oh, I see what you
Yeah,
mean.
yeah. Like Tim?
Yeah, I'd be pressed to call it a lecture, but
Well, sort of. I guess it's more of a lecture format.
yeah, I guess.
Whiteboard, that kind of thing.
Yeah.
But yeah, let us know what you think.
Yeah. All right, folks, guys, like, share, comment, subscribe once again if you haven't already. Check us out, Eigenbros on Twitter, Eigenbros Instagram, Eigenbros.com, the website, and then Eigenbros2 on TikTok. And thank you guys once again, patrons. We couldn't do it without you. We greatly appreciate it. If you guys want to become patrons, check out patreon.com/Eigenbros. And anything else, Juan?
No, that's it. Pretty
All right.
much it.
Okay, guys.
See you next week.
See you later.